Mark asked me to tell you a little bit about some of my research, and also with a focus on sort of the story, the human story behind the research. And actually, what I'm going to talk about, so my talk is about the flavor of a cosmic neutrino, and we'll go through each of those words. I think we can do, like, what is the, I think we got that. And so, just to start with, I want to acknowledge the great collaborators that I worked with on this project. So this is actually something that I did back when I was in Valencia during part of that refinement process. But I think it's a fun and interesting detective story about how my field works and how particle theory, astroparticle phenomenology actually works. So just to complete the story a little bit, so I was actually born in New Zealand, in Hobbiton over there, but moved to Quebec City when I was 6. I did my undergraduate degree at Université Laval, then decided I had enough French, and went to McGill, then on to, as Tony said, I went on to Valencia, and then Durham. This is actually Winterfell, but it's pretty similar. And then Imperial College London, which is the home of, as you know, the Empire. Before moving to beautiful Kingston, Ontario. So my field is astroparticle physics, and the reason I went into that is because I wanted to understand everything. And I didn't quite know how exactly to go about that, and it turns out that astroparticle physics is a beautiful way of doing that because we deal with understanding, well, the smallest constituents of the universe, what are we made of at the most fundamental levels, as well as the largest scales in the universe, stars, galaxies. This is a photograph of the entire universe. So we're going to talk a little bit about that. So this whole story starts, I shouldn't look down. Starts in 2012 as I was finishing up my PhD at McGill University. So it was in January. It looked a bit like this. This is James McGill trying to run away. It's a statue, it's not a real person. And I got a phone call from Valencia, from Carlos Peñagay, saying, why don't you come and work for us? We're in Valencia, which is just a couple of hours south of Barcelona. It's on the Mediterranean. We're on the beach. It's beautiful here. We're just sitting here drinking Estrella and doing physics. It turns out that IFIC, the Institute for Particle Physics, is as far away from the beach as you can get while still remaining in Valencia. Looks a bit like this, but still you notice this color. It's called green. That was notably absent here. So I married my wonderful wife, and then we went off to Valencia. And this is where the story starts. So I was working there. I was doing things that were related to what I did as a PhD student, related to cosmology and dark matter. And this hit the science news. So the IceCube neutrino detector found evidence for these high-energy extraterrestrial neutrinos. This made the splash. This is the front cover of Science. If someone tells you they made the front cover of Science, you go, ooh, wow. And my boss at the time, Olga, said, we have to look into this. This is how she started all projects. We have to look into this. So we did. And so to get from point A to B, I need to tell you what a neutrino is and what an IceCube is before we can figure out, what's actually going on. So I'm going to tell you very, very quickly what a neutrino is. I've called it nature's terrible bookkeeper, and you'll see why in a second. So we all know we've heard of protons and neutrons. They make up the nuclei that are at the center of atoms. And electrons, which have a negative electric charge, those orbit the atoms and bind everything together. It turns out these neutrons are not too happy with their lot in life, and sometimes they decay and turn into a proton and electron. And they also spit out this other thing called a neutrino, which looks a lot like an electron, except it has no electric charge. It's neutral. The neutrino means little neutral thing. A proton, when you bind it in certain ways in other elements, can also do this, turn into a proton, a positron, which is an anti-electron, and a neutrino as well. So you get these neutrinos, any kind of nuclear process, you get these neutrinos. Turns out there are 3 types of these neutrinos. Nobody knows why. Or 3 types of these electrons, actually. Nobody knows why. There's the electron here, which this is your regular, everyday electron guy. They do all the heavy lifting. They hold the universe together. There's this other thing called a muon, which doesn't live for very long. It lives for about 1/millionth of a second. That can exist in high-energy collisions between particles. So these are your space cowboys. They're about 200 times heavier than electrons. They'll show up, zip around at the speed of light, and then decay into a shower of other stuff. And from time to time, you get your tau, which is even heavier, about 3,500 times heavier than the electron. That's really the 1%. These guys live for less than a trillionth of a second before disappearing. But because of these three, what we call flavors of things that can exist, you also get these three flavors of neutrinos that interact in processes similar to what produced that electron in that decay we were talking about. So you got your muon, your electron neutrino, your muon neutrino, and your tau neutrino. And why do we call them tau neutrinos, muon neutrinos, and electron neutrinos? It's because every time I make a muon, I have to make a muon neutrino as well. Every time I make a tau particle, I have to make a tau particle as well. Actually, a tau antiparticle. And every time I get rid of a muon, if it decays, I also wind up with a muon neutrino. Every time a tau decays, I wind up with a tau neutrino. And we see this happening in the atmosphere a lot. So really high energy charged particles from outer space come in, hit the atmosphere, produce loads of stuff, just because they have a huge amount of energy, E equals mc squared. You wind up with a lot of mass. And that stuff turns into muons and electrons, and every time that happens, you get a muon neutrino or electron neutrino. We see this a lot. So if every time you produce a muon, you produce a muon neutrino, every time you produce a tau, you produce a tau neutrino, that means that these neutrinos are actually like bookkeepers. They're counting the number of electrons, muons, and taus, these weird particles, that exist or have ever existed in the universe. That's really neat, right? Except there's a problem with this. As Art McDonald told us, and as was confirmed by the Swedish Academy, these guys don't like to remain in the same state that they started. So actually, as they travel, they'll oscillate from one flavor to another. So your space cowboy turns into a regular Joe, turns into a 1%, so your electron, muon, and tau neutrino, those guys all, I think it's done. They're changing from one flavor to another as they move through space. This is a much better animation than I am able to make by Stan Yen. So here the electron neutrinos are strawberries, and you can see them turning into different flavors, notably watermelon neutrinos and orange neutrinos. This lasts for an entire minute. I've watched the entire minute several times. It never gets old. Unfortunately, I don't have time to do this. But what it means is, if we look at really, really high energy neutrinos that come from outside of our galaxy, they're going a long way. They're traveling a very long distance. So the flavor that you get at the end doesn't really depend on the flavor that you started with. They're going to average out. They're going to turn into some random either electron, muon, or tau. And what you wind up with, if I put a graph of this, so this corner would be all electron, all muon, or all tau, I should wind up with something in the middle here. There's some error bars that look suspiciously like the South Island of New Zealand. I don't know what that's about. But you should wind up with something in the middle. All right. So next we need to talk about how we find these things. So what we do is we go to Antarctica, not we. Other people deserve the credit for me. Nothing to do with this discovery. So you go to this place called the IceCube Neutrino Observatory. An IceCube is actually a cubic kilometer of ice that's located a kilometer below the geographic South Pole. And the reason to do that is because that ice is extremely clear. And what you do is you sit there and you wait. And if a neutrino comes in and hits a nucleus in the ice, so a proton or a neutron inside the ice molecule, the H2O, that H2O is going to explode. This happens very rarely, but it happens. And it'll produce a flash of light. This light is called Cherenkov light. The same kind of light you see in nuclear reactors. This blue glow is going to be the same blue glow. It's going to be much, much fainter because it's just one little neutrino causing this. And these little detectors here that you've stuck in the ice will detect that light. And what it actually looks like when you look at a reconstruction of what the detector sees, so each little dot on these strings is a detector, and the size of a blob is how much light it saw from a given event. So you're going to see a spherical blob when a neutrino comes in, it causes this proton to explode. But there's one thing that happens if it's a muon neutrino, and that is these muons actually live long enough to escape the detector, and they just barrel out. So it comes in, turns into a muon, because every time a muon neutrino is destroyed, it creates a muon. And that muon, which is like a heavy electron, zips off, smacks into a bunch of stuff, and leaves a track. So you have tracks and showers, and from that we can tell what the flavor of the cosmic neutrinos are, to some degree, because the muons are producing tracks. And for this equal flavor ratio, we expect about 25% tracks and 75% showers. Just for reference, that's the size of one of these events. This is Madison, Wisconsin. It's about the size of Kingston. So these are pretty big. So IceCube observed these things for the first time in 2013. And we're nice enough to provide all of this data. Don't bother looking at these. But you can see the event type here, shower, shower, track, shower, shower, track. And we noticed that no one had really bothered counting how many showers and how many tracks there were. And well, they did, but they made one assumption that didn't quite work. Right? So these are 28 neutrinos that they saw. 7 of them are tracks, 21 are showers. Quick math. That's 25% of 28, 75. We expect 25%, so it's all good. Except, remember these guys. So whenever a cosmic ray, whenever something hits the atmosphere, it produces this shower of muon neutrinos. This is where my animation skills really show you one physicist and not an animator. But all of these, so most of these, actually something like 90% of these neutrinos that we get from these atmospheric collisions are muon neutrinos, and we know there's going to be some contamination in the sample. And what we actually find when we directly incorporate this, and I'm oversimplifying a little bit, is something unexpected. So we noticed this, and then we had to do the calculations correctly. We actually had to do the work. You can see there are a lot of, this is a sample from those 3 weeks of just my inbox. So 20 emails, 52 emails, 81 emails, 67 emails. So this is Sergio and Olga emailing back and forth. This may have happened once. I want to apologize. Just so you know that we actually did something serious. Here's some fancy-looking equations. If you know what this means, it's actually a nice, concise way of writing this down. It's the language that we use. But what we found was that if you look at the data, what the data are telling us, so black here in this graph means most favored, and white means disfavored. And if you're above this black line, you're in trouble. All of the neutrinos that they'd seen were consistent with electron neutrinos. We expect a third, and we got all electron neutrinos. And this is really weird. So we published this in physical review letters, and if you meet a physicist and they tell you they publish something in physical review letters, you have to say, oh, PRL, oh, well done, because it's very fancy. So what's going on? Why are we seeing only electron neutrinos? So it could be one of 3 things. So we don't understand these oscillations over very long distances. So Art McDonald was wrong. One possibility. Something strange is happening at these energies that changes the flavor that doesn't have to do with this oscillation. It's something more subtle. And both of these would be very exciting. This is what we're looking for. We're looking for some hint of new physics that we can pull on to try to discover some more fundamental laws. In this case, well, the most likely explanation is that there's some kind of error in the instrument or in the analyses that were given to us that wasn't accounted for. So we did some more. So this caused a splash. A lot of people said we discovered that IceCube didn't exist or something. It's not true. What if some of these tracks were just misidentified? What if the identification rate of these tracks, of these muons, was not correct? So if we included that in the analysis, it brought our fit. Remember, black is most favored. So our expected point now here is in this black region. So we published this second paper on February 9th, 2015. And then on February 11th, 2015, IceCube officially came out with a remarkably similar figure to what we found, including that misidentification effect. And we do know for a fact that this was spurred on by our previous analysis. So this doesn't sound great. Oh, you found out something was wrong. But really, we found some source of error that wasn't accounted for. That means that now that we know this, we can do a much better job in accurately determining the flavor composition of these neutrinos. And that means that with new data, now we have about 120 of these, not 28, we can go in and see if we can find little discrepancies, see if we can find that little thread to pull on, to see if we can maybe discover something unexpected about these neutrinos. So the collaboration wasn't bad. I was invited to speak there in 2017 about getting theorists and experimentalists to talk to each other and sort of iterate on these processes and what kind of thing that we need. This was the title slide of my talk, which included a pub in London called The Astronomer, which is not where most of our group meetings were held, only some of them. And then in 2018, I actually joined IceCube, the Empire, as an associate member. So I'm actually working with them on similar kind of things. So that's the story. Thank you.